In René Magritte's famous painting The Treachery of Images, we see a pipe with the caption, "Ceci n'est pas une pipe." This is not a pipe. Of course, it isn't, it's an image of a pipe, a representation. The painting reveals something profound. Language doesn't point to intrinsic truth, it points to agreed upon meaning. Take the letter A. What is it? It's just a symbol, a squiggle on a page or sound in the air. But we all agree it means something. Yet, in itself, A has no intrinsic meaning. It is simply a shared convention, a token we assign meaning to based on usage. Now take the number 1. Surely that has intrinsic meaning? But ask, 1 what? 1 goat is not 1 cow. 1 second is not 1 kilometer. 1 moment is not 1 molecule. Just like A, the symbol 1 has no meaning in isolation. Its value, its truth, emerges only in context. In this light, the difference between language and mathematics collapses. Both are languages, both are constructed, and both are games we play. This realization cuts to the core of our reality, and to the limits of reason itself. Wittgenstein shattered the illusion that words captured truth directly. Instead, he argued that language is a game, a system of rules that lets us interact, infer, and construct shared meaning. But crucially, he also showed that words don't mean anything in isolation. A is just a sign agreed upon by a group of conscious beings. Without that agreement, it is meaningless. The same holds for numbers. 1 is just as arbitrary as A until we define its use. Hence, mathematics is also a language game. But here's the paradox: if language doesn't contain truth, how can mathematics be so uncannily precise in describing reality? Here enters Gödel, with his incompleteness theorem, showing that no formal mathematical system can prove all truths about itself. There will always be truths that escape the rules of the system. This doesn't make mathematics useless, it makes it human. It reminds us that truth isn't inside the system, it is extrinsic, perceived by the observer. The act of defining axioms, whether in language or mathematics, is like choosing the rules of the game. And within those rules, we build systems that model reality. These models are powerful, predictive, and, crucially, approximate. Wittgenstein told us we are playing games. Gödel reminded us those games are incomplete. Together, they reveal something profound. Language doesn't express truth, but it can approximate it, with the right rules. This leads us to a philosophical question: is language a priori, discovered, or a posteriori, invented? Here, Kant gives us guidance. He argued that certain concepts, like space, time, and causality, are built into the structure of the mind. They are a priori intuitions. But the particular tools we use to engage with them are invented. So we may say, language as a concept is discovered. It is the tool conscious beings use to communicate and interpret the world. But any specific language, English, Hindi, mathematics, logic, is invented, a constructed system built on signs, sounds, and shared rules. The same goes for mathematics. The idea of using structure, quantity, and logic to model reality is a priori. But particular equations, Pythagorean theorem, Schrödinger equation, are inventions within the rules of a chosen game. Words are not reality. Numbers are not reality. They are maps, and the map is not the territory. And yet, we can build incredibly accurate models of the universe. Why? Because language, when constructed carefully, allows us to model relational truths. And mathematics, in particular, is a form of language optimized for precision, coherence, and abstraction. Imagine saying, water is composed of hydrogen and oxygen. You can express that in plain language, or in mathematical notation as hydrogen oxide. Both express the same concept. But the mathematical version is more elegant, unambiguous, and scalable. It's this precision that gives mathematics its predictive power, not that it contains truth, but that it plays the language game better. Not because it is truth, not because it is innate, but because it defines its terms more precisely than other languages do. It creates a formal system with clear relationships between concepts. Within that system, we can construct models that reflect observed patterns in nature. In essence, mathematics works because it plays the language game with fewer loopholes. And when new phenomena challenge its models, as quantum physics or relativity did, we adjust the game, we redefine axioms, invent new symbols, and update the rules. That is how science progresses. That is how language evolves. That is how truth emerges, not from the signs themselves, but from the game we play with them. So, is language capable of expressing truth? Not intrinsically, because symbols alone are meaningless. But extrinsically, through agreed rules and shared contexts, we can use language to approach truth. This is the paradox we must accept. Language cannot capture truth, but it is the only tool we have to approach it. Mathematics, then, is not truth, it is a well-played language game. The better we define our axioms, the more powerfully we model reality. And the closer we get to understanding the universe, not because we have discovered it in full, but because we have described it well. In the end, the true nature of language is this: it is not an objective window into the world. It is a subjective tool, evolving, relational, and inherently paradoxical. But when played well, the game of language, and especially mathematics, can make reality comprehensible. If your mind enjoyed this, engage with Braingasm pages, like, share, comment, and subscribe.